told you about our joint work with Pavel, in which we show only context-free recognition in OMB time. This was presented at CPM last year. But I will tell you, at the end you will see why I decided to show this problem today, because it will be there will be some open problem related to this talk. But first let me describe the problem itself and what do we want to solve. So we are given a context-free language, which is defined as a tuple of four elements, so non-terminals, terminals, a set of production rules, and starting non-terminal. And the most basic, like classic example is a grammar describing the correct bracket, right? So a sequence of brackets is correct, either it's a correct sequence, or it's composed of two correct bracketing sequences, or there are two brackets enclosing some smaller bracketing sequence, right? So this is the whole set of productions for correct bracketing. And here we have only one non-terminal S and terminals that are these brackets, right? And for us, so this is the general definition, and it's not that easy to work with as the so-called Chomsky normal form, in which we have additional constraint that all productions are either two non-terminals or a single terminal, right? So here this bracketing sequence is not of this form, but we can change it adding some auxiliary non-terminals. So there will be this non-terminal O and P and C, standing for opening non-terminal, not the opening bracket, closing bracket, and something temporary in the middle, right? So here it slightly changes. We have more non-terminals, the same terminals, but the grammar is the same. So for now, all the time we'll think that the grammar is in Chomsky normal form. And now let me define the problem that we'll consider today. We are given a context-free grammar that we will think of constant size, and in offline setting, we are also given a string, and we need to determine if the string belongs to the language. So that's it for the offline setting, but we'll consider actually the online one, in which the string is revealed to us. I don't know what's that, I hope it's supposed to be like this. So we are given a string and it's revealed one character at a time. So after seeing every character of the string, we need to say if the prefix of the string up to this position already belongs to the language or not, right? So we have n bits of output, not the same. And now let me describe you the history of this problem. So we have the classic CYK dynamic algorithm from early 60s, and then it has been improved by only logarithmic factors. Later appeared lower bounds for combinatorial algorithms, and we have the best one so far is that there is no combinatorial algorithm that runs in truly subcubic time. And in this work, we will show the algorithm that runs in n cube divided 2 to omega square root of log n. So this is better than shading any number of logarithms, but worse than any polynomial, right? So it's still worse than n to 2.9999, right? And just one more comment, that there is an important result by Valiant that was later also described by Ritter, in which they show that the offline version of the problem can be solved in n to omega time by reduction to matrix multiplication, right? So the omega stands for fast matrix, for the complexity of fast matrix multiplication. And here is this asterisk that these lower bounds, they hold for the offline variant, and then they immediately translate to the online version as well. Okay, so now let me briefly describe you the CIK dynamic algorithm, which will fit on this single slide. It uses the following observation.
In the online version, is it OMB hard?
That's a very good question.
Okay.
So I don't know. Yeah, so we will show how to use OMB, but we don't know if it has its own. Yes, so that was a little spoiler. Yeah, So now let me describe you how the basic algorithm works. So it uses the following observation, right? So if we know that one non-terminal produces an index, and then a different non-terminal B produces another index that is neighboring to this one. So and we know that there is a production from non-terminal C to non-terminals A and B. It gives us that non-terminal C produces index from I to J. Okay, so this is clear, I hope, and this already gives us the following dynamic algorithm for checking which non-terminals produce every index of the string, right? And so this basically goes from the definition. And what's also useful about this approach is that it works also for the online case, right? Because if we do the loops in the right order, we actually can solve the online case in the same running. And so this gives us already cubic algorithm for the online case as well. And then let me tell you briefly what happened in the variance algorithm that runs in n to omega time. So then what they do is they calculate this dynamic programming first recursively for first half of the string, then second half of the string, and then we need to merge the results, right? So basically, while merging, we process all strings that contain the middle element. And the difficulty here is that we will be able to extend the index kind of in both directions. So either we add something to the right of the current character or to the left, right, left. So this is this kind of hard part of merge, right? And then what he observed is that when we think about extending the index to one side or the other, it is not important what's the other endpoint of the index. So let me describe first the picture. So here a node ij will store all non-terminals, producing the index from position I to j. And then the edges down will correspond to extending the word to the left, so adding something at the beginning. So when we have dot ij and go to I prime j, it means that we move the left endpoint, but the right endpoint doesn't. Okay, and what's useful here, and we remember this definition of how these production rules can be applied here, is that when we move from ij to I prime j, so we extend to the left, we do not care what's the right endpoint, right? Because we only need to know which non-terminal produces the index. We don't care about the endpoint itself. So then this, we can see that there is some underlying graph, and then we will calculate its transitive closure using fast matrix multiplication. So yes, this is what Valiant did here, which allowed us to obtain n to omega time. And again, why this is matrix multiplication? Let me just rephrase this observation a bit more precisely. So we want to test. So we can test if we can extend one index to another based only on the non-terminal producing, independently on the endpoint, right? So then, how does it work? So when we have index ij produced by non-terminal y, and there is another non-terminal z that produces another index to the left from I prime to I. We don't care about j, right? Now we learn that non-terminal x produces this whole index. Yes, I hope it's clear that this is this kind of jumps that we will create, and then those we'll be able to have multiple jumps, right? So first we go to I prime, then I double prime, and so on and so on. So this will be the jumps that we do, and here is the matrix multiplication. Of course, it's an algorithm described in a nutshell, but that's the intuition that I wanted to give you from their algorithm.
Sorry, just to clarify, for the last slide, you said you compute the transitive closure of this graph. But it's not by black box. The big graph is too big, is that correct?
No, you have quadratic size.
But then shouldn't it be like 2 omega? Like the number of nodes in this graph is n squared, right? On the previous slide.
Yes, but for us, the nodes will be, because what is here is important for us is that this jumps in the, okay, that's a good question. Let me describe it in detail. So indeed, there are quadratic number of nodes, but the main property here that we use is that the jumps here do not depend on the other endpoint. So we can think only about jumps to the left. So there are essentially n different nodes that are interesting for us, and n jumps to the right.
Okay.
Right, so we kind of compress this graph to n nodes.
Okay, that makes sense.
Yes, but very good
There's
question.
some repeated squaring.
Yes. So then there is divide and conquer, of course, for this divide and conquer to this halving, iterative halving. But then the main idea here is that this graph has this nice property that the edges are not arbitrary. Right, all these jumps in one direction, for example. Okay, so that's why here is the matrix multiplication. And now let me move to the online variant. So my graph, the intuition here is that the new character of the string that will appear will correspond to the new column or in the considered matrix or the graph. Right? So then it means that the natural tool that we will use will be the online matrix vertex multiplication. Of course, it's now like high level intuition, right? So let me remind the problem. So here we are given a matrix and by n and the sequence of vectors, right? And we need to say what's the result of multiplication this matrix by this vector before seeing the next vector. And we know from SOLA 17 by Larsen and Williams that this can be solved in n cubed divided by 2 omega square root of log, right? So this is the complexity that I already mentioned and explained. And also, there is already hypothesis by Monika Henziger and others, in which they conjecture that there is no truly subcubic time algorithm for answering n queries of this. Okay, so this is what we know about this problem. And now let me show you how we solve this context pre-recognition using online matrix vector. Because it's not that there is just a single matrix that we will add columns one by one. We need to see what's happening in this variance approach and kind of tweak it so that we can use this OMV but in a bit smarter way. So what we will do is that we will divide the current prefix of the string into powers of 2. And for every segment, so for every interval of length that is a power of 2, we'll create something that we call the process. And then this will be like a structure that will consume kind of queries, and then will answer some information about more and more infixes. Right? So the queries for a single interval will be pairs, will be information about some so pairs of position I and non-terminal E, which means that this non-terminal E produces the infix starting at position I and ending at the current position T. Okay, and then what we will calculate, we will want to calculate all infixes that start within our interval and end at the position T. So then we will like extend and calculate more and more infixes like this. Like this is the first infix that we'll calculate that starts in our interval and ends position T. And then all longer up to this one that starts at position P and ends at position T. Right? So this is what happens in a single process. And then we will add one character and then the process will kind of update to learn what happened. And then we show that it takes total s cubed divided by 2 omega square root of log. So that will be like a single process. And then in the algorithm, we will, while processing the tip character, we have these processes of smaller lengths, and this process will work, that will output something that will be input to the next process, and the next process, and so on. Right? So here is written a bit more precisely what we get, what we compute. But what's important is that the input to J process is basically the output from all these other processes, the smaller processes that are up behind him. So then what's happening is that process of length 2 to k will be created every n divided by 2 to k queries and will run for at most 2 to k queries. So the total running time is of all the processes in our structure is exactly what we want. So this is our algorithm, and then side comment is that there is like what we have to like develop or extend this OMV to is that something that I like call dynamic OMV, in which in every query we get also the next column of the matrix and the vector that will multiply it. So the matrix is not like super static, but it also gets vector and vectors at the end, right? And so formally we will process in this time. So like every time we aim at this running time, so there will be a sequence of vectors such that we get the new vector of the matrix and new vector of the query, right? So we will have to calculate this bigger product of this query vector with bigger and bigger matrix, and we can solve it in the same way as before. So we'll divide the process matrix into some matrices of sizes that are powers of 2, and then for each of the little squares, we'll build the OMV data structure. So this is like another layer, but essentially the same thing. Okay, so this is what we needed to solve this problem. And so, long story short, we reduced context-free recognition to multiple instances of OMV, right? So, and because of this logarithms do not really matter, this complexity, we have the same range, right? So now, what's this natural open question? Tajabol already asked this question. What's actually the complexity of this problem, right? So this is something that we don't know, and I think that here there are many people who might have interesting intuitions or ideas for this problem, because yes, we don't know the reduction from OMV